Thank you for the invitation to speak. My name is Ilya Kofman, and I will be speaking about a volumish theorem for alternating virtual links. This work is joint with Abhijit Champanerkar. So this work is motivated by an open problem in geometric topology: how to relate diagrammatic and geometric invariants of links. And for the knot 818, its diagram is on the left, and on the right is a picture from Snappy of horoballs in hyperbolic 3 space for the knot complement. And you can see that there are numerical and polynomial invariants on both sides of this divide. And there are some famous conjectures, like the volume conjecture, which relates these 2 points of view. And so one of the first proved results that related diagrammatic and geometric invariants involved the twist number. So let D be a prime alternating diagram of K, and we'll say that 2 crossings are twist equivalent if they form a bigone or a clasp after flips, if necessary. And the twist number is the number of twist equivalence classes of D. D is called twist reduced if twist equivalent crossings are grouped in twist regions. And in this figure, you can see that the twist number is 3 because there are 3 twist regions. Now, Manasco and Thistlethwaite showed that all alternating diagrams of K are related by flips, so the twist number is an invariant of K, which we'll denote by T of K. Now, the volume bounds was a famous theorem by Lackenby, where for a D, a prime alternating twist-reduced diagram of a hyperbolic link, the hyperbolic volume is bounded above and below by essentially the twist number with some linear factors. And the lower bound was improved by Agel, Storm, Thurston, and the upper bound was improved by Agel and Dillon Thurston. And these involve the volume of the regular ideal tetrahedron and the volume of the regular ideal octahedron. And as in all of these kinds of theorems, the upper bound is easier. You just need to find a particular triangulation. The lower bound involved some really deeper ideas that involve the guts of a surface, of a 3-manifold cut along an essential surface. And using the guts, which is the volumes of the hyperbolic pieces, Lackenby was able to show that the twist number is involved in that lower bound. So in the case that the diagram has no bigones, then the twist number is just the crossing number because every crossing is in its own twist region. So for these kinds of knots, like 818, the volume is just linearly related to the crossing number, right? Because it's just, every crossing is essentially in its own twist region. So using these results, Dasbach and Lin showed that they proved a theorem that they called the volumish theorem. And this is the theorem that we're going to generalize. So what they did is they related the twist number to the coefficients of the Jones polynomial. So if you have a hyperbolic alternating knot, so for any alternating knot, the extremal coefficients are 1. And what they showed is that the subextremal coefficients give you the twist number. And then the volume is related linearly to these subextremal coefficients by this formula. And so they used this result of Lackenby. So here's an example. If you take the knot K11A9, then we can see its Jones polynomial here, and we can see that its subextremal coefficients are 2 and 3, so the twist number is 5. And then we can see the 5 twists are right here. So here's one twist region. Here's another twist region. One here, one here, one here. So these are the 5 twist regions. And the volume is given by the formula. The volume can be computed, for example, by Snappy, and it's within the bounds guaranteed by the theorem. So our theorem is a generalization of a type. So for a closed orientable surface, F, with some genus. Let K be a non-split oriented link in the thickened surface that admits a cellularly embedded, strongly reduced WGA diagram on the surface at level 0. And let tau of F be the homological twist number of D. So then let JK be the reduced Jones-Kruskal polynomial. So that's a one variable polynomial where we set Z equal to 0, right? So JKT of 0 is where we set Z equal to 0. And then the homological twist number is given by the sub-extremal coefficients of that polynomial minus 2G. And tau is an invariant of the link in the thickened surface, and F cross I minus K is hyperbolic with these bounds. So in this talk, what I'd like to do is basically explain the terms in this theorem and give you an idea of how it's proved. So these are the various terms that are I need to go over. So the outline of the proof is that the twist number is determined by the reduced Tate graphs on the surface F. That's the first step. The second step is that the certain Kruskal polynomial coefficients express the cycle rank of a ribbon graph, and certain reduced Jones-Kruskal polynomial coefficients express then the homological twist number. And then finally, we'll show that the homological twist number provides bounds for the hyperbolic volume of F cross I minus K. So this is kind of an outline of the rest of the talk. So to start, Tate graphs are, go back to the beginnings of knot theory by Tate, and a planar alternating link diagram is equivalent up to mirror image to its Tate graph. So if you start with a Tate graph, you can, by the medial construction, putting a crossing at every edge, you can recover the knot or link diagram. And then by checkerboard coloring the diagram, you can get the Tate graph. Now there's a choice here, and the other checkerboard coloring gives you the planar dual of the Tate graph. And in this example, the B graph is shown. So this is refers to the Kaufman bracket A smoothings or B smoothings. So similarly, we can talk about a Tate graph on a surface. So a surface link diagram is cellularly embedded if the regions F minus D are disks. And then we have a Tate graph for any cellularly embedded alternating link diagram D on the surface F. And again, we have a Tate graph coming from the checkerboard coloring, and the other checkerboard coloring gives the dual of the Tate graph on F. And here we show the A graph, which has a 2-cycle and a loop. So a crossing is nugatory if the A graph or the B graph has a separating loop on the surface at that crossing C. And we'll say that a surface link diagram is reduced if it is cellularly embedded and it has no nugatory crossings. We say, so in general, so for a planar diagram, nugatory crossings are removable, but for diagrams on surfaces, they're generally not. And we will say that D is strongly reduced if the A graph and the B graph have no loops at all, separating or not separating. And any reduced alternating surface link diagram is checkerboard colorable. So we're going to use two theorems by Bowden and Karimi. The first is they showed that if you have a non-split alternating link in F cross I, then any connected reduced alternating diagram D on F has minimal crossing number, and any two reduced alternating diagrams have the same rive. And then very recently, they showed that any non-split link with a cellularly embedded alternating diagram on a surface has minimal genus. So the basic connection to virtual links is that there are 3 sets that are in bijection. So one is virtual link diagrams modulo isotopy and virtual Reidemeister moves. The second set is links in thickened surfaces modulo ambient isotopy, diffeomorphisms, stabilizations, and destabilizations. And the third is surface link diagrams, for a given surface modulo isotopy, Reidemeister moves on the surface, and handle attachments and removals on the surface. So in addition, a virtual link is alternating if and only if it can be represented by an alternating surface link diagram D on F. So if D is reduced alternating on the surface, Bowden and Karimi's theorems imply that the crossing number and the ride are invariants of the virtual link. So later, when we compute the Jones-Kruskal polynomial on a minimal genus representative reduced alternating diagram D on the surface F, we will get an invariant of the virtual link K. Okay. All right. So let me start with the basic idea that, and a motivating example, that we can get the twist number from the Tate graphs. So if we have an alternating diagram D on the torus, like as the one shown, here we see that the twist number is 2, right? There's sort of these two obvious twist regions. So here are the two graphs. So in red is the A graph and in blue is the B graph. And you can see they intersect at each crossing. Now the A graph has 6 edges with 3 parallel edges because of the left twist region. And we identify the parallel edges to form the reduced A graph, GA prime, which now has 4 edges because we delete 2 edges from GA to get GA prime. Now similarly, the B graph has 6 edges with 3 parallel edges because of the right twist region. And the reduced B graph has 4 edges because we delete 2 edges from the B graph to get the reduced B graph. So this kind of motivates the following lemma. So the twist number is then going to be all of the edges in the A graph, which is equal to the number of crossings, minus the number of these deleted edges from the A graph, and minus the number of the deleted edges from the B graph. So that will leave 1 edge or 1 crossing per twist region. And so that's what we're trying to count, the number of twist regions. So then if we do a little algebra, we see that the twist number is given by the Euler characteristic, and then using the Euler characteristic, we see that it's just the first Betti number of the reduced A graph plus the first Betti number of the reduced B graph minus 2g. So those are also called the cycle rank of the reduced A graph plus the cycle rank of the reduced B graph minus 2g. So this is an expression for the homological twist number using these reduced Tate graphs. The key point is that how do you define edges to be parallel? And we define 2 edges to be parallel if they are homologous on the surface F. So parallel non-loop edges connect the same vertices, but parallel loops may be disjoint. And to get the reduced graph, G prime, we will delete all but 1 edge in each set of parallel edges in G such that the vertex sets are unchanged. So then 2 crossings are homologically twist equivalent if their corresponding edges are parallel in either the A graph or the B graph. And the homological twist number is defined as the number of homological twist equivalence classes of crossings of the diagram D. So each homological twist corresponds to 1 set of parallel edges in the A graph or the B graph, which is one edge in the reduced A graph or the reduced B graph. Okay, so if we come back to our earlier example, we see crossings in each twist region are homologically twist equivalent because pairs of parallel edges form these null homologous 2 cycles. You can see the null homologous 2 cycles. Right, so we see these disks here, and we see another disk on the B graph, for example. So these disks show these null homologous 2 cycles. So that kind of justifies our decision to delete these edges and consider parallel edges like this. However, there are other kinds of homologically twist equivalent crossings. So, and this is going to be an issue. So let's consider these two alternating diagrams projected to two different surfaces. So I'm just looking at the projections and kind of forgetting about the crossing information. Now in both figures, the red crossing and the blue crossing are homologically twist equivalent. Let's take a look at this. So over here, if I make a vertex here on this region, and I can see a loop this way and another loop this way. So these two loops are giving you, these are the parallel loops, right? So these are the homologous loops. Over here, we can see if I put a vertex here and I go around, and I come back here, this is a null homologous two-cycle. So there's a null homologous two-cycle and a pair of null homologous loops. So these are the kinds of situations where we could get homologically twist equivalent crossings, but of course neither pair of crossings forms a twist region. So it turns out that these are the only kinds of issues that come up. And so if D is a strongly reduced, twist-reduced alternating diagram on F, so remember, strongly reduced means no loops. And T is the number of twist regions, and tau is the number of homological twists, basically. Then we have this relationship. And so the homological twist number, the usual twist number, which just counts the twist regions, is going to be between the homological twist number and twice the homological twist number. And moreover, if the genus of the surface is, right, so if the genus of the surface is 1 or the representativity is at least 5, then they are equal. So the representativity being at least 5 means that the boundary of every compressing disk of F intersects the diagram D in at least 5 points. Okay. So, and the idea of the proof is that if the A graph and the B graph do not have loops, then the homological twist number is equal to the usual twist number, only when, well, I guess I should say they're not equal, only when the A graph or the B graph has one of these essential null homologous two cycles without two valent vertices, as in the previous example. So that kind of example captures what could go wrong when to explain when these two kinds of twist numbers are different. So let me change gears here. So we kind of have this idea of homological twist number in terms of the Tate graphs. What I want to talk about now is polynomial invariants of graphs. And so the Tut polynomial is the first and sort of most famous polynomial invariant of graphs that captures more information. So of course, maybe probably historically the first one's the chromatic number, the chromatic polynomial. The Tut polynomial captures the features that we want to talk about. And so one of the things is that it can be defined in a number of different ways, such as contraction deletion, can be defined as a state sum over all subgraphs, and it has a spanning tree expansion over all spanning trees where you assign weights to edges with respect to each spanning tree. It also satisfies a duality that for the if you have a planar dual, you can immediately see what its Tut polynomial is by this relation. And so this was in 1954. In 1987, Thistlethwaite defined a spanning tree expansion for the Jones polynomial by showing that if you have an alternating link, then the Jones polynomial is essentially the Tut polynomial with a variable change using the Tate graph of the knot or link. And so there's a monomial factor there besides this variable change, but it's essentially the same polynomial. And what's amazing is this gap of more than 30 years, there's really no reason why the Kaufman bracket wasn't discovered right after the Tut polynomial, because all of these basic things that we have in knot theory for the Kaufman bracket, like the Skane relations, all come from these contraction deletion operations on the Tut polynomial. So it's quite amazing that it took 30 years to make this jump. And then Bolobash and Reardon extended the Tut polynomial to a 3-variable invariant of oriented ribbon graphs called now it's called the BRT polynomial, the Bolobash-Reardon Tut polynomial. And Dasbach, Futter, Kalfagiani, Lin, and Stoltzfus showed that for any link, not just an alternating link, the Jones polynomial can be recovered from the BRT polynomial of the A graph. So thought of as a ribbon graph. And Krushko extended the Tut polynomial to a 4-variable invariant of oriented ribbon graphs called the Krushko polynomial, and he emphasized its duality property. By using 4 variables, it had this very nice feature, this duality property that I'll talk about. So let's talk about the Krushko polynomial. So if G is a graph which is cellularly embedded in a surface, let H be its spanning subgraph with regular neighborhood. Then consider the number of components, the genus of the subsurface, the regular neighborhood. And what that means is that you're basically taking the regular neighborhood that has some circle boundaries and you're capping those off with disks. Consider then the genus of the complementary subsurface, where you cap that off with disks, the boundaries as well, and think about that genus. And then let K be the dimension of the kernel of this subgraph on the surface. Then the Krushko polynomial is defined as the sum over all spanning subgraphs, H and G, by using these values on each subgraph. And what's happening here is that these 4 variables, x and y, are essentially the same as the Tut polynomial x and y, and u and v are the variables that capture the topological embedding of the graph. So Krushko showed that this polynomial satisfies contraction deletion and a duality relation, given in this way. And then we are going to use a substitution. So this is going to play an important role in what we're going to do next. And so if we let x be x minus 1 and y be y minus 1, then to keep track of this, we're going to use capital letters. So capital P, capital X, capital Y, capital U, capital V in the substitution. So that'll be with the substitution. It makes it kind of clear which polynomial, which version of the Krushko polynomial we're talking about. So here's an example of the Krushko polynomial on 2 graphs with the same underlying graph, but they're of course different as ribbon graphs. They're topologically embedded in a different way. So you can see these are 1 vertex graphs with 2 edges. And so the vertex contributes a V, right? Because the complementary subsurface is the torus, has genus 1. The loop just contributes a 1, and there are 2 of them, so you get 2. And both loops together, that's where you see the difference. So when you have both loops together, the regular neighborhood on the left has genus 1, so that'll get you your U, and the regular neighborhood on the right does not have genus. That's going to be a genus 0 regular neighborhood. And in addition, there is a kernel when you embed that in the surface. So that has a 1-dimensional kernel, so you'll get a Y there. And so the 2 polynomials are different. They're V plus 2 plus U and V plus 2 plus Y that capture the difference between these 2 graphs. So this is the kind of sum that's involved in computing the Krushko polynomial. So now, if we let, so now we're going to look at the coefficients of the Krushko polynomial and use them for the purposes that we need. So let G prime be the reduced graph. And what that means in this context is we're going to delete all but 1 edge in each set of parallel edges and delete all the null homologous loops such that the vertex sets are the same. And then let L be the set of loops. And so we're going to get these 2 quantities. Mu is the first Betti number of the reduced graph without loops, and lambda is just the number of loops. And although G prime is not uniquely determined because you're deleting these loops and it depends on what you're deleting, but nevertheless, mu and lambda are invariants of G. And so the theorem that we proved is that if G is a graph embedded in a surface, then if K is the number of null homologous loops and N is the number of vertices minus the number of components, then the Kruskal polynomial with those substitutions has the coefficients mu and lambda exactly on these terms. So I'll explain the idea of this theorem in a bit. But the first thing I want to do is show that we can apply this theorem with Kruskal's duality to the take graphs, to the A graph and the B graph. And so these are dual. So for a reduced alternating diagram, D on the surface F, if n is the number of vertices in the A graph minus 1 and capital N is the number of vertices minus 1 on the B graph, then we'll get these mu and lambda for the A graph and mu bar and lambda bar for the B graph. Then mu, lambda, mu bar, and lambda bar are exactly the coefficients of the Kruskal polynomial of the A graph given in this way. And you can see that by this duality, like for example, mu and mu bar are exactly, you can see these variables changing from v to u, from x to y, and so on. So you can kind of see how the duality comes from, this corollary comes right from the previous theorem by duality. Okay, so let's take a look at an example. So here's the virtual knot 4106, and here's the its diagram on the torus, and you can see the blue graph is the B graph, the red graph is the A graph, and you can see the reduced B graph. We just take a pair of parallel edges, and there will just be one edge there, and the A graph is already reduced. The two loops are not parallel, and the two edges are not, right? It can't be reduced then. Okay, so we have here mu, lambda, mu bar, and lambda bar on the, for the reduced B graph and the reduced A graph, okay? And then you can see that they are playing exactly the role as claimed on the coefficients. So from the theorem, we get these terms v plus 2x plus u plus y, and they are showing up in exactly as claimed in the Kruskal polynomial for the A graph. Okay, so that's an example. Okay, so let me give you an idea of the proof of the theorem for the mu case. So this is for the mu variable. Let E prime be an edge in the reduced graph without loops. So a non-loop edge in the reduced graph. And let's call that an edge class for the m parallel edges in G. So then for these edges in the edge class, we can look at the spanning subgraphs Hj in G with exactly j edges in that edge class and no other edges. So then the weight on that spanning subgraph Hj is going to be given as this Vg, xn minus 1, y, j minus 1. And that's actually pretty clear. That's easy. You can see it only has those j edges. So for example, it'll have a j minus 1 dimensional kernel. So that's that y to the j minus 1. The connectivity is explained because you're only connecting those two vertices. That's that exponent on x, and so on. So that's clear that that's the weight on Hj. If you sum over all of the weight, all spanning subgraphs Hj of this type, and add up all of their weights, then you'll get all of the different possible j's, and then there are going to be m choose j such subgraphs with this weight Vg xn minus 1, y, j minus 1. And now what's interesting is that if you pull out this factor out front, you will just get a binomial expansion that gives you the polynomial on the right. Okay? So you'll get this factor and this polynomial on the right. So every non-loop edge contributes this expression to the Kruskal polynomial. Now with the substitution, x going to x minus 1 and y equal to y minus 1, this simplifies. So the 1 plus y becomes just a capital Y, and the y in the denominator becomes y minus 1. So now you can see that as a series and actually perform this division, and you get this expansion. So you'll get this factor VGXN minus 1 with this series right here. Okay? So every non-loop edge E prime, right, contributes this expression to the Kruskal polynomial. And for the unique graph with no edges, just vertices, that has weight VGXN. So if you do this substitution again, then that graph H0 contributes minus n to this term VGXN. So again, we're looking, right, so we're looking just at this piece right here, right, and we've got this guy right here. And so we can see, we can put these together, and the coefficient is going to be on this VGXN minus 1 is exactly going to be the number of edges in the reduced graph without loops minus n. Now we remember that n is just the number of vertices minus 1. So by Euler characteristic, that's just the first Betti number of the reduced graph without loops, which is just mu, which is what we wanted to prove. Okay, next. We are going to consider another coefficient in the Kruskal polynomial, and for this we need another definition. So pairs of loops are called genus-generating loops if the genus of the regular neighborhood is positive. So for example, here is a ribbon graph with one vertex with 4 loops, and you can see, for example, this pair of loops is a genus-generating pair of loops. So on a surface, they might be embedded in some complicated way. So there's a picture there that the embedding might be more complicated, but you can see the genus right from the ribbon graph. So gamma is going to count the number of pairs of genus-generating loops in the reduced graph. Okay. There's another thing that we need to count, which is triples of loops, which we're going to call 3-petal loops. So a triple is are 3-petal loops if no pair of loops in that triple is parallel, and they have positive genus and a positive kernel. So for example, here's an example of a 3-petal loop on a torus. So here are three loops that together have positive genus. So, right, so if you take a regular neighborhood, that'll have genus 1 on the torus, and if you put it on the torus, then it'll have a positive kernel. Right, so you'll have a longitude and meridian in this diagonal, and that'll give you a positive kernel as well. So the lemma is that if G has no 3-petal loops, then the Kruskal polynomial has this coefficient, where gamma is the count of these pairs of genus-generating loops. So this gives, it's the same kind of argument as in the previous argument, where we're just counting, we're counting these genus-generating loops now. Okay, so the next idea is to use the Jones-Kruskal polynomial. So the Jones-Kruskal polynomial so comes out of this idea by Kruskal of the homological Kaufman bracket. So it's the sum of states on the surface where we assign another variable z to capture information about the homology of the state circles. So K is the dimension of the kernel of the state circle sitting on F, and R is the dimension of the image in the homology of the state circles. Now, since state circles cannot intersect, this R is going to take its highest value as the genus of the surface. So the highest exponent on Z is going to be the genus of the surface. So Kruskal normalized this to form a polynomial which we're going to call the Jones-Kruskal polynomial. And then Bode and Karimi showed that there is a reduced version the reduced part is right here. So this is the reduced part. So the reduced Jones-Kruskal polynomial is a link invariant by the property of Bodin and Karimi, who showed that the rive is an invariant of the link K in F cross I. So if you know that, then you can do this normalization and get a link invariant, which we're calling the reduced Jones-Kruskal polynomial. And this is due to Bodin and Karimi. So we can get this polynomial from the Kruskal polynomial of the A graph by a particular substitution. And that result uses, this was basically known to Kruskal. This is in Kruskal's paper. So you can get the reduced Jones-Kruskal polynomial as a specialization of the four-variable Kruskal polynomial, just like you can get the Jones polynomial of an alternating link from a specialization of the Tut polynomial. This is in direct analogy. Okay. So now we have a theorem that gives some more information about the coefficients of the reduced Jones-Kruskal polynomial. So if K is a link in F cross I with a reduced alternating diagram such that the A graph and the B graph do not have three-petal loops, then, as before, we're going to let mu, lambda, and gamma be as before for the reduced A graph. So mu is the cycle rank of the reduced A graph without loops, lambda is the number of loops on the reduced A graph, and gamma is the number of pairs of genus-generating loops in the reduced A graph. Mu bar, lambda bar, and gamma bar are the same thing for the B graph. Then the reduced Jones-Kruskal polynomial has exactly these coefficients. Okay, that's the theorem. And as a corollary to the theorem, so if D is a reduced alternating diagram on F, such that the number of genus-generating loops of both the A graph and the B graph is 0, then the homological twist number is a link invariant of K in F cross I. And the idea of the proof is that if the homological twist number is just given by the cycle rank of the reduced A graph plus the cycle rank of the reduced B graph minus 2g, which is just lambda plus lambda bar plus mu bar minus 2g. So when gamma and gamma bar are both 0, we show that the above terms are distinct, right? And so the homological twist number tau is just given by the coefficients of the reduced Jones-Kruskal polynomial, which is then a link invariant. So that's the idea. Let's take a look at some examples. So here's an example of a four-component virtual link. And here you can see mu and mu bar. So the A graph and the B graph are both the same. It's a self-dual because self-dual ribbon graph by the symmetry. And you can see it has these 3 cycles. So mu and mu bar are both 3 and there are no loops. So the theorem predicts that the coefficients are going to be exactly this 0, 3, 3, and 0. And you can see in the reduced Jones-Kruskal polynomial for this virtual link, it's exactly as predicted. You'll just see the 3 and the 3 there for mu and mu bar. So you can get the homological twist number as just 3 plus 3, right? Minus 2, because 2 times 1. And that's going to be 4. And that is the correct, of course, twist number because there are these 4 crossings, each in its own twist class. Okay. So let's come back to this 4106. For 4106, well, the issue is that you have this gamma equal to 1, right? So, right, there is a pair of genus-generating loops in the A graph. And because of that, you will get a 0 right here, right? So you know that mu is also 1, and that gives you the 0 right here because mu minus gamma is 0. And so the issue then is that the homological twist number tau is going to be given by, you know, this lambda plus lambda bar plus mu bar minus 2g, which we know is 3, right? But because gamma is 1, you cannot read the homological twist number directly from the coefficients of the reduced Jones-Kruskal polynomial, right? It's this issue right here, that the two quantities contribute to the same coefficient in the reduced Jones-Kruskal polynomial. So that's the problem here. Another example on the other side is the virtual knot 4105. So here, it kind of looks like a virtual 818. You can see that it has this B graph, which is the blue graph, and when you reduce it, when you take out the parallel loops, you can see one pair of genus generating loops, and so you can see that this gamma bar is 1, and therefore you'll see these quantities exactly as predicted. The issue is that because gamma bar is 1, the homological twist number cannot be computed directly from the coefficients of the reduced Jones-Kruskal polynomial. Let me just point out quickly that from the diagram on the left, it's not apparent that the homological twist number is 2, but on the torus, it becomes clearer because you can see these disks. So here's a disk, so that these two crossings are in a twist class, and then these two crossings are also in a twist class. So here's another disk right there. So that tells you that there are actually only 2 twist regions. So the homological twist number is 2, even though from the diagram on the left it may not be apparent. Okay, so the last part, I want to talk a little bit about hyperbolicity. So if the genus is 1, then this is straightforward. We say K is hyperbolic if T2 cross I minus K admits a complete hyperbolic structure. If this exists, the geometric structure is unique, has finite volume, and then K as well as the boundary tori become cusps. Topologically, T2 cross I is the complement of the Hopf-link. So what happens then is that the link complement, T2 cross I minus K, can be written as a link in S3 with a Hopf sublink. So you can kind of use the Hopf sublink to get that T2 cross I. So here's an example of that 4-component virtual link that we saw before, and you can put that in S3 as a link complement in S3, right, with this extra Hopf link. And if you use Snappy or if you use geometry, you can see that there's a complete hyperbolic structure with 4 regular ideal octahedra for this link in S3, and therefore for this link in T2 cross I. So the issue becomes, what happens if the genus is greater than or equal to 2? So then F cross I minus K in general does not have a unique hyperbolic structure, but we can say that K is TG hyperbolic if it admits a complete hyperbolic structure such that the boundaries, the F boundaries, are both totally geodesic. And then that hyperbolic structure is unique, that complete hyperbolic structure is unique, and if it's TG hyperbolic, we can associate a unique hyperbolic volume to the link K. So Colin Adams with a group of undergraduates proved that if you have a reduced alternating diagram, so on the surface of higher genus, then D is prime, if and only if it is obviously prime. So that means that it doesn't have a disk that contains some crossings and intersects the diagram in 2 points. And if D is prime, then F cross I minus K is TG hyperbolic. So a corollary is that a non-classical virtual alternating link that has a prime diagram D on F for G, right, for genus at least 2, coming from its alternating virtual diagram. So if that's the case, if it has such a prime diagram, then it is TG hyperbolic. And then in their paper, they also computed hyperbolic volumes of all virtual knots with up to 4 crossings. So, okay, let's now come back to our theorem. So this is the theorem that I stated at the beginning. And now we understand many of the terms that are here. So in particular, we need a cellularly embedded, strongly reduced WGA diagram. What's a WGA diagram? This is a term that I think is due to Josh Howey. And the idea of a WGA diagram is that there's some condition on it being prime. So this is something they call weakly prime. And there's a condition on the representativity of the diagram. It needs to be at least 4. So if you have a cellularly embedded weakly prime diagram, right, with a certain representativity, then that's a weakly generalized alternating diagram. And you need all those conditions to get the lower bound on the volume. That's where the harder geometry is, to show the lower bound, to use exactly this guts machine of Lackenby to prove those kinds of results. Okay, so what I want to do now is focus on just the first part of the theorem. So on the first part of the theorem, we see that a condition, D being strongly reduced, means that there are no loops in the Tate graphs, right? The A graph and the B graph. So if it's strongly reduced, lambda and lambda bar is 0, and then of course gamma and gamma bar are 0, there are no genus generating loops. So the homological twist number is mu plus mu bar minus 2g. And in that case, we show that the mu and the mu bar are exactly the reduced Jones-Kruskal coefficients. And this is just, again, doing the substitution, coming from the Kruskal polynomial, and showing that those are the right coefficients for mu and mu bar. So the second part of the theorem, hyperbolicity and the various volume bounds, follows from a theorem of Kalfagiani and Purcell, where they showed the volume bounds in terms of the usual twist number. And we know how the twist number is related to the homological twist number. And in particular, the fact that the usual twist number is less than twice the homological twist number means that their bound of 6 Viac has to be adjusted to twice that. So that's the doubling right there. And then the rest goes through, because what happens is that, of course, right, if on the torus, they're the same, and this issue only occurs on the higher genus surface. So that's the essence of the proof of our theorem. Let me also make a remark. At the same time as we were doing our paper, Bavier and Kalfagiani proved a similar result, and they proved the invariance of the usual twist number, the number of twist regions, using another part of the Kaufman bracket-Skene module of the surface, F cross I. So the idea here is that the Kaufman bracket-Skene module has a basis of all multi-loops on the surface, including the empty multi-loop. So if you let D0 be the coefficient in the Laurent polynomials of A of the empty multi-loop, that's just the contractible state circles on the surface F. Now you can normalize that using the Rive to get a Jones-type polynomial, which is this normalized invariant of the link in the thickened surface. And then using the Euler characteristic of the guts of the 3-manifold cut along the checkerboard surfaces and properties of adequate diagrams, they proved that the reduced, this twist number is coming from the subextremal coefficients of this J0, this normalized polynomial, minus 2g. So it's a very similar formula. And the difference is that the reduced Jones-Kruskal polynomial, Jk of Tz, when we said z equal to 0, uses states on F that are null homologous, including non-contractible states. And so we saw that the homological twist number differs from this usual twist number exactly when the genus is greater than or equal to 2, and that's when the reduced Jones-Kruskal polynomial with z equal to 0 is going to be different from this type of normalized invariant when genus is greater than 2, greater than or equal to 2, and that's exactly when these two different notions of twist number are different. So I should add that I don't know anything about this J0 I don't know anything about its coefficients or any other information about this polynomial. The Jones-Kruskal polynomial is a much more well-studied invariant. And let me end with a question. So if D is a reduced alternating diagram on F, then we proved a corollary that if gamma and gamma bar are 0, so there are no genus-generating loops in either take graph, then the homological twist number is a link invariant of K and F cross I. This condition is necessary for our proof, but maybe it's not necessary. So if D is a reduced alternating diagram on F, is the homological twist number tau a link invariant, even if these gammas are not 0? Or another way of asking this question is, for any alternating virtual link, is the homological twist number an invariant of the virtual link? So that's open because of this restriction that we have on having no genus-generating loops. So thank you very much. That completes my talk. Thank you for your attention.